I'll just use that. Yeah. Okay. All right. Now it should work. First of all, I want to thank the organizers for all the work they did to provide this opportunity for all of us to be here in this nice place and to meet and to work, and for the opportunity to speak here in particular. So I'm going to speak about rotation numbers of one-parameter families of cocycles, or sometimes they're called fiber-wise rotation numbers. I will present several results. Okay, I will present several results joined with Victor Klepsen, and some of them are joined both with Victor Klepsen and Pedro Duarte. This whole project started when, together with Victor, we realized that some of the regularity results regarding stationary measures of some random dynamical systems are suspiciously similar to some of the results about regularities of density of states measures in the spectral theory. And we were trying to find some connection. And Pedro Duarte, who is an expert in both dynamical systems and spectral theory of discrete ergodic Schrödinger operators, was trying to explain us on a hand-waving level why that connection should be actually there. We were trying to make sense of it, and now a couple of years later, we think that we have some level of understanding, and that's what I wanted to report today. So before to define the fiber-wise rotation number, let me recall the notion of the standard rotation number. So first of all, let's agree that for the next hour, we will only consider orientation-preserving homeomorphisms and diffeomorphisms of the circle. So if you take one, then intuitively, rotation number is just the average shift of the orbit along the circle if you apply the rotation again, applies your homeomorphism again and again. In order to make that that notion formal, what you want to do, you want to consider the lift of that homeomorphism. So the universal cover of the circle is a line. So the lift of the homeomorphism is going to be a map of the line into itself. So what you do, you just pick a point, apply that lift, and see how fast your orbit is going to infinity. So it was known already to Poincaré at the end of the 19th century that the limit always exists, doesn't depend on the initial point, and that point is natural to call rotation number. Notice that in this definition, in that limit, we have some freedom of choice of the lift. The lift is not unique, and any other lift will be different, can differ from the original one by an integer additive constant. So if you change the lift, your rotation number, your limit here will change by that integer constant. So it makes sense to consider the rotation number just mod 1. So the rotation number is just a point on the circle. Great. So let's recall some basic properties of the rotation number. First of all, rotation number is equal to 0 if and only if your homeomorphism has a fixed point, which is easy to understand because if you have a fixed point, then it prevents your orbit from moving around the circle. If you have rotation number which is rational, then you can just pick that rational, then the homeomorphism must have a periodic orbit. So you can just take that periodic orbit, and the way it goes around the circle will be completely dictated by its combinatorics. So it will be, rotation number will be rational with denominator equal to the period. Also, rotation number is invariant under the topological conjugacy. If the conjugacy is orientation preserving, if it's orientation reversing, you are risking to get the minus rotation number. And finally, the rotation number depends continuously on that homeomorphism. Okay, all that is contained in most of the textbooks in dynamical systems. Another property is the following. Let's include our homeomorphism into a one-parameter family of maps. So the easiest way to do that is just to take any homeomorphism of the circle and take the composition with the rotation. So the rotation angle is going to be our natural parameter. So you have a one-parameter family of homeomorphism. So what you can do, you can consider the rotation number of the corresponding homeomorphism as a function of the parameter E. So you can ask what the properties of that function. So first of all, we know that this function is continuous, just because the rotation number depends continuously on the homeomorphism. Also, in this specific case, the rotation number is going to depend monotonically on the on the parameter because you always add the rotation into a specific direction. And therefore, you will get some function like this. So, of course, the function will depend on the initial homeomorphism. If you take, for example, the identity maps, then the rotation number as a function of the parameter will be just linear. But typically, you will get something like a contraset or devil's staircase. So what you have here is that you have infinitely many flat parts in the graph. And those flat parts appear because your diffeomorphism or homeomorphism, well, let's talk about diffeomorphism. Your diffeomorphism can have a periodic orbit which is attracting or repelling, but hyperbolic. As soon as you have a periodic orbit which is hyperbolic, by small perturbation of that diffeomorphism, you cannot change the fact that you will still have a periodic orbit of the same period nearby. And therefore, the rotation number will be completely determined by the combinatorics of that periodic orbit. So to the whole interval in the space of the whole interval in the graph, which is going to be the flat interval. All right. What we want now, we want to generalize the notion of the rotation number to a more general context. So what I'm going to do, I'm going to consider a cocycle, circle cocycle over some base dynamics. So what we are going to start with, we will take some measure-preserving transformation. Let's assume that it's ergodic. And for simplicity, let's assume that it's just a homeomorphism of a compact metric space, such that the support of the measure is the whole space. Let's consider homeomorphism attached to each point on the base. And let's consider the skew product. So you have some dynamics in the base. You have fiber, which is a circle. And you apply along the orbit of this of your dynamics. So when you take more and more iterates, you compositions of those homeomorphisms along the orbit. What is natural to do is the following. You can pick a point on a fiber, and then you can see average how far you under the Thank you. So we will choose a lift for each homeomorphism on the fiber. And we're going to consider the lift of the whole cocycle. And now we're going to consider the cocycle where you have a line as a fiber, and on each step you apply the corresponding map on the line. Now, notice that in this case, even if the initial cocycle was continuous with respect to the point in the base, it's quite possible that you cannot choose those lifts to be continuous with respect to the initial point. So we're not going even to try to choose them continuously. We'll just say that they are going to depend measurably on the initial point. And moreover, even for the initial setting, we will allow to consider the cocycles that depend measurably on the point in the base. And now we'll do exactly the same things that we did for the rotation number. We will just take the product composition of those lifts. We will see how far our point goes along the line, and we will take the average. So it's not hard to prove that the limit is going to exist for almost every initial point in the base, and moreover, the limit, if it exists for some point on the line, it will exist for any other point on the line and will not depend on that point. So it seems like we define something reasonable, right? So let's try to see what happens if you take a different collection of the lifts. If you take a different collection of the lifts, then for each specific homeomorphism, the lift is going to be to differ from the initial lift by an integer constant. But that integer constant could be different for different points. So we have integer-valued function, measurable function on our space. And if you look at the rotation number that is defined by a new collection of lifts, you will get something that differs from the initial rotation number by the corresponding integral. And now it's a disaster, because we have an integral of an integer-valued function, measurable function, and that integral can be anything, which means that our rotation number gives us zero information about our dynamics, because by the change of the lifts, we can change it any way we want. So rotation number is no longer defined. Well, in order to turn that failure into something useful, we're going to make the picture more complicated. We're going to include our cocycle into one parameter family of cocycles. And if you have some choice, if you made some choice of the lifts initially, then we will certainly assume that our initial cocycle depends continuously on the parameter. We can choose the lifts also to depend continuously with respect to the parameter. In this case, even if we choose a different collection of the lifts, then the difference of the rotation numbers defined in this way for different values of the parameter is going to be well defined. Because in this case, each of the rotation numbers after you change the lift will be changed by some constant, but that will be the same constant for both of them. So that constant will cancel each other, and therefore the difference is going to be well defined. The situation is kind of similar to what you have if you consider the antiderivative of a continuous function. If you think about some function but only allow me to know something about antiderivative, and if I ask you about the value of antiderivative at a given point, then the answer gives me zero information about the function. But if you give me the information about the value of antiderivative at two different points, that already gives me the information about the integral of that function. That's exactly what's happening here. All right. Now, this is a little bit paradoxical situation because the definition that I just gave is certainly purely dynamical, but people who studied that notion are mostly not from the dynamical systems community. So the reason for that is because that notion appears naturally in the spectral theory of discrete ergodic Schrödinger operators. And in order to explain the connection, I want to make a very, very short 5 minutes crash course on discrete ergodic Schrödinger operators. So let's forget about dynamics for a moment. There will be a moment when I will say let's forget about spectral theory. So let's consider a self-adjoint operator of this form on L2 of z. Now, the first two terms of this operator form the Laplacian. So usually the discrete Laplacian is u of n minus 1 plus u of n plus 1 minus 2 u of n. But notice that the term minus 2 u of n can be incorporated into the last term into the potential, and that's what people usually do. So as soon as you have any bounded sequence of numbers that we will call a potential, this formula defines a self-adjoint bounded operator, and therefore the spectrum of that operator is going to be a compact subset of the real line. So we're interested in that spectrum, but of course if you don't put any restrictions on the sequence of numbers, you don't prove anything useful, so you want some context. So the class of the potentials that you want to consider depends on the physical problems that you want to solve. For example, if you want to study the quantum dynamical properties of the amorphous materials, then you want to get potential which is a random sequence. If you want to study metals or crystals, you want a periodic potential. If you want to study quasi-crystals, you want a potential that mimics the properties of that material. So, for example, substitution or Sturmian sequence. So all that people did consider, and all those examples fit nicely into the same framework of discrete ergodic Schrödinger operators. So what we want to do is the following. Let's take some dynamical system. Let's take some continuous function on that dynamical system. It's traditional to multiply that continuous function by some constant that is called coupling constant, and people study the dependence of the spectral properties on the strengths of the potential in terms of coupling constant. And you can think about that in this way. So you pick some initial condition, you start going along the orbit of this dynamical system, you read off the potential, you read off your observable, and that's going to be exactly your potential that you will plug into that formula for the operator. Now, what you want to prove results of the form for almost every initial condition you have such and such spectral properties. Now, in order to be able to say for almost every condition, of course, you want some measure. So let's assume that our transformation is measure preserving, and the support of our measure is the whole space. And let's also assume that our measure is ergodic. So that's our setting. So just to give a few examples. For example, if you want random potential, if you just flip a coin and put the potential to be equal to 0 or 1 depending on the outcome, then it's called Anderson-Bernoulli potential, and it fits nicely because you can just consider the Bernoulli shift and Bernoulli measure and the function that is just the value of the 0 element of the sequence. Or if you consider almost Monsieur operator, then it's just a rotation of the circle, and the observable is just cosine or some trigonometric polynomial. Or if you want to consider one-dimensional quasi-crystals, the most prominent model is so-called Fibonacci Hamiltonian. It's given also by the rotation of the circle, but the function takes only 2 values. What is nice about that potential is that it's both given by some substitution and also belongs to the realm of Sturmian potentials at the same time. So that's why physicists use it a lot. But for us, the specific, for this talk, the specifics are not important, just to give some examples of the ergodic potentials. Okay, now we want to define the Schrödinger cocycle. And we're going to do that in the following way. First of all, let's pretend that we don't know that our operator does not have to have eigenvalues. So let's assume that it does have an eigenvalue, some eigenvalue E, and let's try to find it. If it has an eigenvalue E, then for that E, we have a difference equation, which is usually called stationary Schrödinger equation. And as usual for difference equations, we can reduce that to the products of matrices. So the difference equation, if instead of a sequence of numbers that gives you the solution of the equation, you consider the sequence of vectors that give you pair of subsequent solutions, then those vectors are related in this way. So that corresponding matrix is called transfer matrix. And it's easy to see that the determinant of this matrix is equal to 1. So you have SL to R matrix there, and what you do if you want to find the whole solution of the difference equation, you just fix 2 values, U0 and U1, and then you just multiply that by the product of matrices along the orbit of your dynamical system. That's exactly what Schrödinger cocycle is. It's SL to R cocycle defined by that potential and the collection of SL to R matrices of that form. Great. As soon as you have SL to R cocycle, every SL to R matrix defines a projective transformation. One-dimensional projective space is a circle. So we have a circle cocycle. And moreover, we already have a natural parameter here, which is energy. So we have a one-parameter family of circle cocycles, and therefore we can apply our notion of fiber-wise rotation number. So of course, fiber-wise rotation number is defined only up to additive constant, but all the properties that survive if you add a constant to the function are there. For example, if your function is equal to constant on some interval, that's a property that survives if you add a constant. If the function is Lipschitz, that property survives. If the function has some specific modulus of continuity, that property survives. Now, if your cocycle is hyperbolic, it should tell you something about the spectral properties of the operator. Now, it's pointless in this audience to define what's the hyperbolic cocycle, but I want to remind that specifically for SL2R cocycles, you can actually forget about stable, unstable directions. You can just define uniform hyperbolicity exactly in this way. You just need the products of the matrices along the orbits to be growing in norm exponentially uniformly with respect to the initial point. If you haven't seen it, it's a nice exercise to derive existence of stable, unstable directions for each of the, for such a cocycle. Okay, another notion that we will need is so-called density of states measure. So there are several ways to define it. One of them is the following. Let's take our operator, And let's cut our lattice, one-dimensional lattice. Let's just cut one finite, large finite interval. Then the restriction of our operator to that finite dimensional subspace is going to be a symmetric operator. The boundary conditions are not that important. We can take Dirichlet boundary conditions, for example. And we have finite dimensional operator. The spectrum of that operator is just finite collection of eigenvalues. Those eigenvalues are some points on the real line. Let's just take an atomic measure equidistributed and probability atomic measure equidistributed on the eigenvalues of this finite matrix. It turns out that for almost every initial condition for any ergodic Schrödinger operator, there exists a limit of those atomic measures, weak star limit, and that limit is called the density of states measure of initial family of operators. An alternative definition would be the following. For each initial condition, we have some specific operator. We can consider the spectral measure for that operator, and then we can take the average of all those spectral measures with respect to all the initial conditions. We can integrate with respect to that measure mu in the base. That will give you exactly the same measure. So what is known, so people, yes, it's a theorem. Yeah, absolutely. Usually people in spectral theory work with the distribution function of that density of states measure, which is called the integrated density of states. And what is important for us is that the support of the density of states measure is exactly the spectrum of our operator. A spectrum in a sense that it's almost true spectrum. It's an ergodic family, and therefore there exists some compact set, non-random compact set, such that for almost every initial condition, the spectrum of the corresponding operator is exactly that compact set. That's called almost true spectrum. Okay. So it turns out that there exists a very direct and explicit relation between the density of states, that is spectral property, and the rotation number of the corresponding Schrödinger cocycle, which is a dynamical object. Namely, if you consider the specific form of the transfer matrix, you will see that for large values of energy, whether positive or negative, the corresponding cocycle is necessarily uniformly hyperbolic. Which means that for large values of the energy, if you change the energy, the rotation number is not going to change at all. Also for so we can choose, in particular, we can choose the generators in such a way that the rotation number is just 0. And it's natural, so just again, out of the explicit form of the Schrödinger cocycle, if you take the continuation when energy goes to minus infinity, you will see that the rotation number in this case will be equal to 1/2 at minus infinity. And once again, it's a theorem that the integrated density of states is expressed just in this way via the rotation number of the cocycle. And now we can forget about the spectral theory, and now we can just think about the rotation number of the Schrödinger cocycle and try to understand something about the spectral properties of that cocycle. All right. So from here, we can describe the spectrum exactly as a set of energies for which, by a small change of the parameter, you do change the rotation number of the cocycle. So this is a purely dynamical description of the rotation of the spectrum of the ergodic family of operators. On the other hand, if the cocycle is hyperbolic, then by a small change of the parameter, you cannot change the rotation number. So it's natural to ask whether it's true that hyperbolicity is exactly the criterion for the energy not to be in the spectrum. And that's exactly the case. This is so-called Johnson's theorem. Johnson's theorem claims that the spectrum is exactly the set of the parameters for which the Schrödinger cocycle is not uniformly hyperbolic. And now we definitely can forget about spectral theory. Now we can just ask the question, how can you describe the parameters, how you can describe the locus of hyperbolicity in the space of all the SL2R cocycles. So, of course, you don't have to restrict yourself to the case of Schrödinger cocycles. So notice that we have three different properties. One property, given energy, is in the spectrum, or not in the spectrum, better to say. Another property, the cocycle for that energy, Schrödinger cocycle, is uniformly hyperbolic. And the third property, by a small perturbation of the energy, the rotation number of the cocycle doesn't change. So two of those properties are purely dynamical. And of course, it's very natural to think that those two properties are related even for the cocycles that are not Schrödinger cocycles. And that was kind of a folklore statement, and people who needed that statement every time would add an appendix to their paper proving that statement in that specific form. So for example, Daniel Lenz proved it for the base which is strictly ergodic, or Chris Marks proved it for the case when instead of Schrödinger cocycles you consider the cocycles defined by Jacobi matrices. Or in the paper by Avilboki and Damanik, they had an appendix where they proved it specifically for cocycles that are homotopic to a constant and where the parameter is introduced exactly by the angle of the rotation. So you start with some cocycle and then compose cocycle on each fiber with a rotation, and the rotation angle is your parameter. Just several days ago, I talked to Nicolas Gourmillon, and he said he pointed me to his recent preprint where he announced that even for nonlinear case, there is an analog of that statement. So if you have a cocycle given by circle diffeomorphism, not necessarily projective, then there is some dynamical description of the parameters for which the rotation number doesn't change. So just to present an explicit statement, I want to give the statement that we provided with Victor as an appendix once again in our paper. And the statement is the following. So let's consider SL2R cocycle. Let's assume that this cocycle is actually not just a cocycle, but a family of cocycles with some compact set of parameters. So what we can do, we can assume that this cocycle is monotone, which means the following. If you pick any vector and consider its image, when you change the parameters, the image is going to move exactly in the same direction for every fiber and for every point on the circle. So then we can define the rotation number. And it turns out that the rotation number is over some open set is going to be constant and not going to change with the parameter if and only if the corresponding cocycle is uniformly hyperbolic for each parameter in that interval. Yes. Any homeomorphism of a compact metric space with some invariant ergodic measure. Just continuous, yes. Just continuous. You don't need it. So all you need is monotonicity, strict monotonicity, and you don't need any smoothness. Okay. So that's just to give one example of purely dynamical statement that is inspired by the statement in the spectral theory. And several people already mentioned Jacob Pollis, so I want to mention the pictures that Jacob Pollis used in some of his lectures, because this is exactly the context in which we are working. So in one of his lectures, he said that in the 70s, the picture of the world of dynamical system was very simple. There was a hyperbolic dynamics, and there was some small, strange portion, dark realm that we didn't quite understand, but it was really small. In the 90s, after a tremendous improvement in our understanding, the understandable part of hyperbolic dynamics started to be really small, and the dark realm started to be really large, but also some pieces there started to be more clear, partially hyperbolic dynamics, non-uniformly hyperbolic dynamics, and so on. So let's think about that picture in the following way. Let's consider the space of all dynamical systems. For example, the space of all Schrödinger cocycles, or the space of all SL2R cocycles. And let's consider the locus of hyperbolicity, the set of dynamical systems that are uniformly hyperbolic. we have some one-parameter family in that space. So for Schrödinger cocycles, specifically one-parameter family given by the energy. And we want to know how that family intersects the complement to the locus of hyperbolicity. Because due to the Johnson theorem, that intersection is exactly the set of energies that are in the spectrum. So you can think about different bases, and you can think about different pictures that you can generate in this way, and you can think about different results in spectral theory as a reflection of those pictures. You can also add the rotation number. So when you move the parameter along this curve, as soon as you are in the hyperbolicity domain locus, the rotation number is fixed, and as soon as you cross the complement, the rotation number is changing. So that's what's happening. Okay. Now, let me, before I go to the next result about the fiber-wise rotation number, let me go back to the usual homeomorphisms or diffeomorphisms in this case. And let's consider that picture of the rotation number as a function of the parameters that we have seen before. So we already said and explained why this picture is a counter function, but what is the regularity of that function? It's a result by Grachik from 1991 that this rotation number, if your diffeomorphism is at least C2 and it's monotone with respect to the parameter, then this is going to be a Euler continuous function. So to my surprise, this is not in the textbooks. Also, I believe that this result should belong to the textbooks, actually. But as soon as we know that, it's very natural to ask whether the same statement holds for fiber-wise rotation numbers. And surprisingly enough, the answer is no. Nevertheless, what one can do, one can still find a uniform modulus of continuity for the rotation numbers that are defined in this dynamical way, but that will be a different one. So let's consider our cocycle. The statement is the following. First of all, let's assume that the dependence of each of the diffeomorphism is smooth with respect to the parameter, and the derivative with respect to the parameter is uniformly bounded. Secondly, either let's assume that all our diffeomorphisms are C1 with the uniform bound on the C1 norm, or if we want to allow measurable cocycles, we want the C1 norm not to be too large too often. So that is a specific condition that we need. Then it turns out that the rotation number is necessarily log-Euler regular in exactly this sense. So the modulus of continuity is given by 1 over log of the distance between the parameters. So moreover, this estimate is optimal. It cannot be improved, and there are examples that provide the modulus of continuity that is as close to this one as you want. All right, the proof is surprisingly simple. So here's what you want to do. Let's pick any point on any fiber, and let's consider the images of that point. First of all, with respect to the cocycle given by one energy, and secondly, with respect to the cocycle given by another energy. And let's see how those points are going to differ from each other. After the very first step, since we assume that the map on a fiber depends smoothly on the parameter, we know that the images cannot differ by more than some constant multiplied by the distance between the parameters. On the next step, nevertheless, we can already multiply that distance by some number, which is given by, at most, given by the C1 norm of the corresponding diffeomorphism. And after that, we can also add a little bit that is proportional to the distance between the parameters, but now we can already think about that quantity as about something negligible. On the next step, again, we can apply the diffeomorphism over the next point, and therefore, eventually, you will get an estimate that is given by the product of the upper bounds of C1 norms along the orbit. So if you take the product of numbers along the orbit, then of course you want to consider the sum of logs of those numbers. And of course you want to apply the ergodic Birkhoff theorem, and that's exactly what gives you that bound. That's exactly what gives you that condition that allows you to apply the ergodic theorem. All right, so what happens if you made the full circle? So what happens if after application of your dynamics, say 100 times, you realize that you moved by at least, you moved by 1. It means that after 100 iterates, your rotation number, you added 1 full circle, which means that your rotation number cannot change by more than 100. Because every time we made the worst possible estimate. And if you just work out all the estimates in this scheme, that's exactly the modulus of continuity that you'll get. That's the whole proof. So it's really just several pages. All right. Of course, this proof gives you something, and that something is optimal for some dynamical systems in the base, but for many classes of dynamical systems, that is very far from optimal. Because if you think about 2 nearby points on the circle and you apply the diffeomorphism, then more likely than not, the distance between images is going to be smaller, not larger. Therefore, you should expect a better modulus of continuity for the rotation number. And that's, oh, I'm sorry, I completely forgot the important, most important stuff. So that result was inspired by the result that is well known in spectral theory, and the result is the following. For the ergodic discrete Schrödinger operator, the integrated density of states has exactly that modulus of continuity. So this is a partial case of that more general result. And the proof of that partial case that was given over 40 years ago is actually purely spectral. So people were using so-called Thouless formula, and even if there is a generalization, there is a recent paper by Duarte and co-authors on dynamical Thouless formula, you are still in the realm of projective cocycles. So nevertheless, this is a purely dynamical statement. All right, so as we said, in general, this should not be optimal. So let's consider the following situation. Let's consider the case when you have a random dynamical system. Suppose you have, just for simplicity, let's assume that you have finite collection of diffeomorphisms, and you apply them with prescribed probabilities. And it turns out that, and of course you want to include that into one parameter family, and then you can ask what is the modulus of continuity of the rotation number. So it turns out that for a generic family, the rotation number is going to be Hölder continuous, which is certainly much better than log Hölder. Now, you can ask what does it mean generic family? That means exactly the following. We need to assume that there is no measure on the circle, on the projective space, or well, in this case on the circle, such that this measure is invariant under all diffeomorphisms in our dynamical system. Now, in this case, the rotation number is Hölder continuous. Now, once again, for the Anderson model, it's known that the integrated density of states is Hölder continuous. In fact, in many cases, it's even better than Hölder continuous. Under some additional assumptions on the distribution, it will be Lipschitz, and under some even nicer assumption on the distribution, it will be even C infinity. But specifically for Anderson-Bernoulli case that we consider here, it's going to be only Hölder. Okay. So how would you approach such a statement? So we're going to provide an explicit formula for the rotation number, and we will use that formula to establish Hölder regularity of the rotation number. So in order to provide the formula, we will need to use stationary measures. And the stationary measure for random dynamical system is kind of an analog of the invariant measure, but it means the following. It's such a measure that if you push it forward under all the maps in your random dynamics, and then take the average with respect to that distribution in the space of transformations, you will get back exactly the initial measure. So what we are going to do, we're going to consider stationary measures for forward maps, and we're going to consider stationary measures for backward maps, for inverses. Notice that we used to think that the invariant measure, if it's invariant for a diffeomorphism, it's also invariant for its inverse. For the random dynamical system, if you have a stationary measure forward, it does not have to be a stationary measure backward. So those can be two different measures. And what we're going to do, we're going to take two values of the parameter, and we're going to consider one stationary measure for one value of the parameter, which is going to be a forward stationary measure. And we're going to consider the backward stationary measure for another value of the parameter. And now we're ready to give an explicit formula for the increment of the rotation number. That increment is going to be given by the following. So first of all, I want to define some set on the torus, and that set is going to be the set. Okay, let's think about it in the following way. You pick a point on the circle, you take the image of that point under the first value of the parameter, and then you change the parameter to the second value. That point moves, the image of that point moves and gives you some interval on the circle. So you do that for each point on the circle, you get some subset of the torus. So if you take, of course, that subset of the torus does depend on the specific map, specific point from the support of your distribution for the specific map from your random dynamical system. So what you want to do now, you want to take the measure on the torus that is given just by the product of those two stationary measures, and then you want to take the average, so the expectation of that quantity. What you get is exactly the rotation number. All right, so that will, okay, as soon as we know that our stationary measures are Hölder continuous, if that would be the case, then this formula would imply that the rotation number is Hölder continuous. Indeed, we assumed that the dependence of our maps on the parameter is going to be smooth, and therefore, if you change slightly the parameter, the Lebesgue measure of that set is going to be proportional, roughly speaking, proportional to the distance between the values of the parameter. On the other hand, if the measure that we consider is going to be a Frostman measure or Hölder continuous measure, then it immediately gives you the estimate, which is Hölder estimate on the increment of the rotation number. Now, what the question is, how can we be sure that the stationary measures are Hölder continuous? And this is a recent result joined with Victor Klepsen and Grigory Manakov. The statement is the following. Once again, I will formulate it only for the case when you have finite collection of diffeomorphisms, finitely supported distribution for the random dynamical system, but actually a much more general statement holds. So let's consider that random dynamical system, and let's assume that there is no invariant measure invariant for all of the maps at the same time. It turns out that that's enough to make sure that every stationary measure doesn't have to be unique, every stationary measure is Hölder continuous. And that's certainly applicable to the previous slide, and that gives you the proof. Okay. What is left, I'm sorry, that's, I go in the wrong direction. Okay, what is left here is the question where this formula is coming from. Well, this formula by itself is a partial case of even more general formula. That is, I have only 5 minutes left. That is the following. Okay, let me just show the formula. And, okay, this is a formula for the rotation number, fiber-wise rotation number for any cocycle, circle cocycle. So once again, here we don't have random dynamical system anymore. So what we do, we take any invariant measure for the first parameter for the whole cocycle. We take any invariant measure for the second parameter, and it turns out that it's enough to do the following. Let's take any point on any fiber. Let's consider the difference between the images of those points for two different parameters. Let's measure that interval that we obtained with respect to one of those measures. And let's integrate with respect to that initial point distributed with respect to the second invariant measure. It turns out that what you get is exactly the increment of the rotation number. If you apply that formula to the case of the random dynamical system, which is a partial case of the cocycle with a circle as a fiber, then you will get exactly that formula for the rotation number in the case of the random dynamical system. And I guess it's a good moment to stop. Thank you.
Okay, thank you very much. Any questions?
In some place, you said that the change of variation of rotation number is just Helder. But do you know something about the exponent of the Helder?
No, I actually don't, because in that result that claims that you have Euler continuity of the stationary measure, that's a purely existence result. There exists such an alpha such that you have that inequality. I believe that if you restrict yourself to some more specific situation, for example, for projective cocycles, then you can say more. And the case of projective, the projective case was studied heavily because it's just a theory of the random products of matrices. And I believe that there you actually do have some estimates for the Euler exponent. But here, when you don't have assumptions that it's a projective cocycle, we cannot claim anything specific.
Thanks. Also in this direction, if in the case it's better than just Hölder, can you say something about, does it have some dynamic impact, like a rigidity result, if it's better than just Hölder continuous? If it is better than just Hölder continuous, can you say something?
That's a perfect question, and the answer is the following. It's true that it cannot be better than Hölder continuous uniformly for all the random dynamical systems. It is also true that it is better than Hölder if you have some additional properties on the distribution in the space of your diffeomorphisms. So, for example, in the projective case, if your distribution is absolutely continuous, then you can deduce that your rotation number is actually a smooth function of the parameter.
Other questions? If not, let's thank the speaker again.